By 2025, banks and Bitcoin could be broken by quantum computing.
Quantum computing.
Quantum computing. Well, what is quantum computing? So what is quantum computing? You may have heard this term before, and sure, it may sound like something from a 1980s science fiction television show, but I assure you that although it sounds crazy, we are living in the age of quantum computing. And to really understand what exactly quantum computing is and the implications it has for civilization, we have to take a step back and talk about regular computing, how the systems we know and love currently work, and how quantum computing is such a big divergence from anything that's come before it. And I'm going to do my best here to keep things pretty generalized because I'm not a physicist, and much of the science surrounding how quantum computing works is brain-breaking in its complexity and just general weirdness. So to get started, traditional computers, like the one you're using right now, operate on classical physics. They use binary coding for information, how it's stored and processed through something known as bits. These are the basic units of information. These bits can represent either a 0 or a 1. Think of it like a switch that's either off or on. Everything a traditional computer does, from simple calculations to running complex software, is built upon manipulating and processing these bits. Quantum computers, on the other hand, harness the principles of quantum mechanics to process information in a fundamentally different way. Instead of using bits, they use quantum bits, or qubits. Qubits can represent not only 0 or 1, but also a combination of both simultaneously, thanks to a phenomenon known as superposition. Traditional computing would be like a person flipping a coin, where the coin will land as either heads, representing 0, or tails, representing 1. But a quantum computer is like a person spinning a coin on a table, where it's in a state of both heads and tails at the same time until it's observed. This superposition allows quantum computers to perform many calculations simultaneously, vastly increasing their processing power for certain tasks. Another weird but crucial aspect of quantum computing is a feature that's called quantum entanglement. When qubits become entangled, the state of one qubit becomes dependent on the state of another, regardless of the distance between them. This means that changing the state of one qubit instantly affects the state of an entangled partner, allowing for incredibly fast communication and coordination between qubits. So that's a lot of information, right? How do I put this into an analogy? Well, imagine that you're solving a gigantic jigsaw puzzle with billions of pieces. In a classical computer, it's like you're trying to fit each piece one by one, starting from the corners and working your way inward. It's a slow and tedious process, and if you make a mistake, you have to backtrack and try again with another piece. Now, picture a quantum computer as a team of puzzle solvers with special X-Men mutant-like powers. Instead of each puzzle solver working on a single piece at a time, they can work with multiple pieces simultaneously. They can even try different combinations of pieces at once, exploring various possibilities at absolutely lightning speeds. But here's where it gets really interesting. These quantum puzzle solvers can also share information and collaborate in ways that classic puzzle solvers simply can't. They can communicate instantaneously, learn from each other's progress, and eliminate wrong combinations much more efficiently. So quantum computing is like having a superpowered team of puzzle solvers that can tackle the most complex puzzles by working on multiple pieces at once, sharing insights, and ultimately piecing together the solution much faster than traditional methods. And this parallelism is what makes them potentially much more powerful than traditional computers in various fields. But one area that often stands out is cryptography, particularly encryption and code breaking. Much of our modern world is based on the ability to secure data and information through encryption so that only authorized parties can access that information. It's used extensively to secure sensitive data in communication systems, in banking transactions, e commerce, and many other domains. Traditional encryption methods rely on mathematical problems that are believed to be computationally hard for classical computers to solve. They rely on encryption schemes that leverage the difficulty of factoring large numbers. However, because quantum computers have the potential to break some of these encryption schemes much faster than classical computers, it can be a bit scary of a concept. On the flip side, quantum computing also offers the potential for new cryptographic techniques that are completely resistant to quantum attacks and also offer the potential to establish secure communication channels that are theoretically immune to eavesdropping. So, kind of a glass is half full, half empty situation. In addition to cryptography, quantum computing is also expected to have a profound impact on a lot of other domains, such as optimization, drug discovery, material science, and machine learning. So the upshot is that quantum computing is weird, but it has really big implications for us as a civilization. Well, that's quantum
Quantum
computing
computing.
in a superpowered jigsaw puzzle solving analogy.